All right. Hopefully this is working. I wanted to talk about day 87, and I'm going to move through this pretty quickly. So I know that I'm presenting this in class because I have to be out for the day, but also do realize that I'm going to link this up to the day 87 classwork so you can look at this, pause it, do what you need to do. But I definitely want you to try this and do this because buffers it's a really important concept. It's one of the biggies when we talk about acids and bases and AP chemistry, and you need to know what a buffer can and cannot do, and the definition of a good buffer versus a bad buffer. So, with that, let's take a look at question number one. It says a certain buffer is made by dissolving sodium bicarbonate and sodium carbonate in water. These are two salts. Write the necessary equations to show how this buffer behaves when hydrogen or hydroxide is added to the solution. Translation, when a strong acid or a strong base is added to the solution. Be sure to show both the hydrogen addition and the hydroxide additions, and make sure that these are in separate scenarios. All right, so the first thing that we want to do is make sure that we understand that we are looking at two salts. And remember that sodium bicarbonate looks like this, and it will dissociate into a salt that has a it has a conjugate of a strong base in there, and then the remaining is a conjugate of a weak acid, which is carbonic acid, which is HCO, or sorry, carbonic acid is H2CO3. So we know that conjugates of strong bases don't do anything, so we're going to ignore that. And then we have sodium carbonate, which is NaCO3, and it will dissociate into two sodium ions and also carbonate. So again, the sodium will do nothing. These two salts, like I said earlier, all the salts that we're dealing with right now are conjugates of strong, or I'm sorry, they're strong salt, so they will dissociate 100%. So what that leaves us with is these two ions, and hopefully that you're recognizing that there is a common ion in this. And that's what we want to use for our buffer. And keeping in mind that, hey, when we look at a good buffer, a definition of a good buffer from the video from last night, a good buffer contains no strong acids, it contains no strong bases, but it can absorb a strong acid or a strong base and resist a large change in pH. So there's a lot of caveats that go along with a good buffer. And these two things right here, they are not a strong acid or a strong, or yeah, they're not a strong acid or a strong base. And so they may work out quite well as a good buffer, as long as we don't exceed the buffer capacity. So let's take a look at the two scenarios where we would add a strong acid or a strong base. So I'm going to go ahead and just put the bicarbonate over here. And then on the other side, I'm going to put the carbonate ion over here. And so when I introduce the strong acid, hydrochloric acid, for an example, um, you'll need to be able to ask yourself what side of the equation is it going to go on? Is it going to be on the left side or the right side when we are adding it to a good buffer? And hopefully you said that it would go on this side. And you would be correct because if we add a strong acid to this buffer solution, what the hydrogen is going to do is jump on the carbonate and form more bicarbonate by taking out the excess hydrogen, as long as we have a high enough concentration to absorb the hydrogen that we're adding. Also, keep in mind that we want to make sure that we have a high enough concentration of our bicarbonate, and so that it just doesn't eliminate the hydrogen by just having carbonate ions in there. But again, we're trying to make sure that the pH doesn't change, which we'll see here in some later questions. So this is how the solution handles a strong acid. So let's give another scenario where we add a strong base. So the addition of a strong base would be the hydroxide ion. And so if I add a hydroxide ion, again, I'll ask you, does it go on the left side or on the right side? And hopefully you said it would go on the left side. Why did you say that? Well, because then the hydrogen in the bicarbonate would jump on the hydroxide, forming a carbonate ion, and water. So this is what we commonly think of when we see a neutralization reaction. Both of these were neutralization reactions. In this case, it actually does form water, which we automatically start thinking, well, water is neutral. And yeah, that's one way to think about it. But also, neutralization means that we are controlling any excess hydrogen or hydroxide that's added to a solution. And neutral doesn't always mean 7, a pH of 7. So it kind of means that we're taking care of our solution. For example, our blood doesn't have a pH of 7. It's more on the acidic side. So when we drink things or we eat things that are very acidic or very basic, we have buffers in our own body that helps to regulate that acidity or that alkalinity, the basic stuff. So that's how this solution that has bicarbonate and a common ion, the carbonate ion, can handle either the addition of a strong acid or a strong base. All right. So now looking at question number 2, let me zap this, clear that out. Looking at question number 2, it is saying, okay, we've got part A, part B, part C, part D. And you can see it on your paper. I'm not going to scroll down. But the scenario is we've got 4 different containers that we're starting off with. And what we're going to have in these 4 containers is this is going to be a weak acid. This is going to be a common ion of a weak acid, which, I mean, technically would be a base. We're going to have pure water, and then we're going to have both the weak acid and its common ion in this. Okay. So hopefully you're going to, first of all, calculate the pHs for these. And I would highly recommend trying this on your own, finding out what the pH of each of these 4 containers are. So part A, this is container A, or part A, and part B, part C, part D. So they're not like, we're not blending them. It's not like, okay, we're going from A to B, from B to C. No, I want you to set up 4 containers. And then in question part 3, we're going to add a strong acid to each one of these and find out which of these solutions handles that strong acid the best. Hopefully you're smart enough to figure out which it would be, but I don't want to spoil it for you. All right, so looking at the first part, or part A, propanoic acid. So obviously propanate's not 1 of your 10 polyatomics, but propanoic acid has a Ka value of 1.3 times 10 to the negative 5. Propanoic acid, when it dissociates, it's a weak acid, so it'll dissociate some hydrogen and some propionate ion, okay, as expected. So when we make up our ice chart, this is our 0.1 molar solution. We have none of the hydrogen, none of the propionate initially. And then we'll find out what is our concentration of X at equilibrium. And again, it's the hydrogen that we're focusing on since we're trying to find out what is the pH of this solution at the end of the reaction. So first and foremost, be sure you write an expression. Again, if you have a Ka, make sure that your hydrogen is on top. And then we know that our value is 1.3 times 10 to the negative 5. Rearrange the variables, use the 5% rule. And in this case, we get a pH that's around 2.94. Now, you might say to yourself, 2.94, that seems very acidic. Well, this is an acid. So acids typically have an acidic pH. But I don't want you to be thinking about that right now. All right, part B, we're going to add zero 0.1 more of sodium propionate. And hopefully you're saying to yourself, ooh, we got a common ion here. And you would be correct. Also, this is a salt. How do you know it's a salt? Because you see a conjugate of a strong on this. So, like what we did on the quiz not too long ago, yesterday, and what we did in the homework with the common ion effect, and what we did with, um, uh, oh boy, common ion effect and um, salts. I was like, where was it? The salts, we talked about how these salts behave when placed in pure water. Remember, conjugates of strong don't do anything. However, this is a conjugate of a weak acid, and conjugates of weak acid behave as a base. And so we would expect this salt to cause the water to become more basic, or when we dissolve it in pure water, we become more basic. So with that being said, since we have something that is not an acid, but it's a common ion of a weak acid, we need to find out what its Kb value is. And so make sure you do the Kw is equal to Ka times Kb. We do need to write an expression that has a Kb value. And of course, hydroxide should be on top. And then we're going to solve for X, which in this case would be equal to the hydroxide. So find out what the value of X is, going through all the processes that you're keenly aware of. We got a pOH that's equal to 5.06, but we're looking for a pH. So our pH is around 8.94. Again, this is a conjugate of a weak acid that behaves as a base. So you should say to yourself, this should have a basic pH. And it does. Okay. All right. Pure water. Now, I know that many of you know that pure water has a pH of 7, but you have to be able to prove why it has a pH of 7. You just can't say, well, pure water has a pH of 7. Keep in mind that when we look at the Kw value, it's equal to the hydrogen times the hydroxide concentration, and it has a value of 1.0 times 10 to the negative 14. That is given to you on your equation sheet. You may want to make an ice chart. I would highly recommend it. So we've got water that breaks apart into hydrogen and hydroxide. Not very well, but it does. And it looks like this. So it is pure water, which is a liquid. And we start off with no hydrogen or hydroxide. We add X. We end up with X. And when we plug those into the expression, which we just already wrote there, we have X times X is equal to 1.0 times 10 to the negative 14. So X squared is equal to negative 1.0 times 10 to the negative 14. So to find X, okay, X would be the square root of 1.0 times 10 to the negative 14, which is equal to 1.0 times 10 to the negative 7. So this X represents our hydrogen. So if you take the negative log of our hydrogen concentration, which in this case is 1.0 times 10 to the negative 7, you get a pH that is equal to 7. Now, you might say to yourself, do we really have to do that and justify it? If you're asked to find how pure water has a pH of 7, you better be able to do that. And I wouldn't be surprised if you saw that in May, or if you saw that on a test, or if you saw it on a quiz coming up. Every good AP student should be able to do that. So we have 3 pHs listed. We've got one that's neutral. That is our water here, which has a pH of 7. We have our base, which has a pH of 8.94, and we have our acid, which is a pH of 2.94. So now we're going to find out what is the pH of something that has propanoic acid and sodium propionate. So we're going to take both of those and plug them in. Keep in mind, our propionate ion is like what we did up here. So it's sodium propionate. We don't want to involve the sodium in here. So we're not going to show the sodium, okay? Because a common ion, or I'm sorry, a conjugate of a strong base doesn't do anything. So we're only going to focus on the propionate. Okay. And so when we write our ice chart, we have 0.1 molar of our propanoic acid, and we have 0.1 molar of our propionate. Using the 5% rule, this is beautiful, okay? You may use the Ka expression or the Kb expression. I don't care. Just make sure that when you do, you're using the correct Kb or Ka value. Don't just go rando on this and pick any one of them. The 5% rule, we're able to drop X, which essentially means that we cancel our concentrations. So now when we look at it, our hydrogen concentration is equal to 1.3 times 10 to the negative 5. So our buffer has a pH of 4.89. Now, what I don't want you to think is, oh, the propanoic acid went from a pH of 2.89 to 4.89, or whatever the pH was. No, these are 4 separate containers. One is a weak acid, one is a conjugate of a weak acid, a salt, another one's pure water, and then this last one is our quote unquote buffer, or contains a weak acid and its common ion. If you're interested in using the Henderson-Hasselbalch equation, you are more than welcome to do it. However, you must have concentrations of our common ion and the weak acid at the end. Okay. So in our first scenario up here, where we just had the propanoic acid, we had very little amount of our stuff. And by using 5% rule, we didn't know what our concentrations were. Okay, so by using the 5% rule, whatever this value is here must also be down here. So we couldn't use it in the first one. We also could not use it in the second one because we were solving for x. So that would not work. But in this one, we do have our acid, which is HA in this case. Our propanoic acid is down here. And then we have our propanate ion, which is on top. It is a little bit better, a little bit quicker, but you must show your process. Don't just like write this equation and all of a sudden come up with, oh, okay, it's 4.89. Okay, I know your calculator can do it, but you have to actually set it up and show it. Okay. All right, so now we have 4 containers. So we have a pH of 4.89, we have a pH of 7, we have a pH of 8.94 and 2.94. So there's our constant or our values there. Now what we're going to do is we're going to add a strong acid to each one of those beakers of the solutions we just created. Okay, so keeping in mind that when we look at our initial concentrations here, they do have some values because we already set it up and this is a continuation. So now I have my substance, I'm going to add a strong acid to it. By doing that, in the first scenario, we have our weak acid with very little hydrogen, very little propanate ion at the very end. In this case, we're adding 0.02 molar of our strong acid, and we don't have enough of the propanate ion to absorb all of the strong acid. So what happens is one of these has to go to 0, and then equilibrium will be reestablished, and so we'll shift back. So that's why you see approximately 0, because we're not going to actually solve for that value. However, since the buffer capacity, quote unquote, has been exceeded, there really wasn't a capacity here, we're going to focus on the concentration of our hydrogen when we subtract that value. And so now all we have to do is take the negative log of our concentration of our hydrogen, and we get pH of 1.72. So here's what I want you to think. We started off with the weak acid, we added a strong acid, and hopefully you're kind of like working through and saying, if I add more hydrogen ions to an acid, shouldn't it get more acidic? And you would be correct in saying, yes, it should get more acidic. Okay, so when you add more hydroxide to something, it should get more basic. So if I'm an acid and I add hydroxide to an acid, it should move toward the basic scale. May not get to be basic, but it'll move in that direction. So keep that in your head when you're actually thinking about, okay, I'm adding a strong acid, I'm adding a strong base, or I'm adding a weak acid, or I'm adding a weak base, because we're going to talk about how those behave when we do titrations. That's just around the corner. All right, part B, we're going to add a strong acid to our common ion. Well, this does have enough of the propanate to absorb all the hydrogen, and the hydrogen does go to 0. However, since we didn't have hardly any propanate at the beginning, this is, even though we absorbed all the hydrogen and the pH didn't go crazy, quote unquote, get too acidic, we do have to look at the value of our concentration at the very end. And now we have our concentrations for our propanate, which is 0.08, and we have a concentration of our propanoic acid. When we plug that in, we get a pH of 5.49. Keep in mind, this sodium propanate originally started with a pH of 8.94. So it went from a pH of almost 9 to a pH of almost 6. That, my friend, is a terrible buffer. It went from the basic side to the acidic side of the scale. Now, if you wanted to show the quote unquote old fashioned way of doing it, I would highly recommend it. And even though we're looking at a weak base here, you're more than welcome to use the Ka because again, at the end, you're going to have the propionate and you're going to have the propanoic acid. And so we're just solving for the hydrogen. But it's not wrong if you use the Kb and solve for the hydroxide and then find your POH and then find the pH. So I'm good with whatever way you're showing, just as long as you're showing the work. Okay. All right. Looking at part C, this is a terrible situation. So we have pure water and we're adding 0.02 moles of hydrochloric acid to water. There is so little hydroxide in the solution that this essentially has just changed into a solution that has a 0.02 molar solution of hydrochloric acid. So the pH now with this in pure water is 1.7. So it originally started at 7 and plummeted down to 1.7. And we would expect that because there's no hydroxide in the solution to absorb all of that hydrogen that was just introduced. So yeah, pure water is a terrible buffer. How's that? All right, so then looking at part D, we have 0.1 molar of our propanoic acid. We have 0.1 molar of our propionate. Yeah, I know it changed a little bit based on what we did on the previous step, but we'll pretend that the 5% rule, so we're going to use this. We have more than enough of the propionate to absorb the hydrogen. And so whichever one of these is smaller will go to 0. And in this case, the hydrogen does go to 0. Okay. And so now we have a 0.08 molar concentration of our propionate, and we have a 1.2 molar concentration of our propanoic acid. If you want to use the Henderson-Hasselbalch equation, plug it in, you get a pH of 4.71. Or you can, again, use the equation up here and solve for it. But the key here is now our pH, oh, come on, don't die on me now. Oh, sorry guys, the pen is terrible. Give it a couple seconds here. So I think our original pH for this, if I can remember, it was 4.89. So 4.89 to 4.71. It's not a great buffer to have, but it definitely had the least change in the pH. So when we are answering this type of question, which one had the smallest change in pH, which is question number 4, obviously solution D is the better buffer. It contains both a weak acid, the propanoic acid, and its conjugate or common ion, which is the propionate ion. Solution D shows the greatest resistance to change in the pH when either a strong acid or a strong base is added, which is its primary property of a buffer. All right, so again, take a look at this. I know I went through this rather quickly. It would be to your benefit to be able to work out the buffer type problems. It's not as bad as you think it is. I know a lot of previous students said they hate buffers, but I think it's because we're getting closer to the end or close to the end of the semester and we want to finish strong. So don't give up on buffers. Buffers like you. Hope this helped.